Now, called Not Your Run-of-the-Mill Cosmologist, Max Tegmark explores the complex origins and ultimate fate of the cosmos. The author of more than 200 technical papers, 12 of which have been cited more than 500 times, he has created several of the fundamental data analysis tools, theories, and measurement systems that have advanced modern cosmological study. Elected Fellow of the American Physical Society in 2012, he directs the Foundation Questions Institute and is a professor at MIT. He's here tonight to discuss the content of his new book, Our Mathematical Universe, My Quest for the Ultimate Nature of Reality. In it, Professor Tegmark takes us on an astonishing journey through past, present, and future, and through the physics, astronomy, and mathematics that are the foundation of his work. Most particularly, his hypothesis that our physical reality is a mathematical structure, and his theory of the ultimate multiverse. Combining popular and groundbreaking science, he not only helps us grasp his often mind-boggling theories, but he also shares the triumphs and disappointments that have shaped his life as a scientist. So please join me in welcoming Max Tegmark.
Thank you so much. Thank you so much for having me here tonight. It's a pleasure and honor. I'm here tonight because I want to encourage you all to think big. Because we humans have again and again and again underestimated both the size of our cosmos, discovering that everything that we thought existed was just a small part of a much grander structure, a planet, a solar system, a galaxy, a universe, and maybe even a hierarchy of parallel universes. But we've also repeatedly underestimated the power of our human minds to understand and improve our cosmos. So what do I mean by the first part, that things are getting bigger and bigger? Well, to understand that better, we need to really remind ourselves of what we humans have figured out so far about our place in space during the 13.8 billion years that there's been a space to talk about. So let's begin by taking a little trip up into the universe. Let's get the lights just completely off for this little part. As we leave our planet here, when cavemen were walking around, 20,000 years ago, looking at these sparkling white dots in the sky, they made up beautiful myths for what these stars were. But I think many of them at the same time felt a little bit melancholy, figuring that they would never really be able to figure out for sure what this was. And yet, by 2,000 years ago, Eratosthenes, using just cleverness, had managed to figure out the size of this magnificent planet that we live on. And over the course of the years that followed, we have actually now managed to understand so much more about these mysteries, not with rocket power necessarily, but with mental power, just letting our minds fly. And you see here, the first time this ingenuity also led to us making things fly for real. These are the orbits of near-Earth satellites that we humans have placed there. You see some farther out satellites as well flying around. This is a fully real, accurate ray tracing simulation here, showing everything exactly to scale, made by the American Museum of Natural History in New York. So if you wonder, for example, why you can't see the moon here in its orbit, it's because it's to scale. This is how big things are, so you can't even see the moon when it's drawn to size. For thousands of years, the ancients, to them, the universe was basically our solar system. And they had no idea how far away the stars were. Our solar system, of course, is quite vast. It takes 8 minutes, as you know, for light to reach us from the sun. It takes hours to go across the solar system. But this is still, of course, just a very small part of a much grander structure that's gradually coming into view now, our Milky Way galaxy. I'd like you guys actually to raise your hand if you know anybody who was born before 1925. I do too, my grandma. And it's remarkable to think that it was only in 1925 that Edwin Hubble established that there are other galaxies. This is how recently this expansion of our perception of the cosmos happened. We now know that the solar system is just a small part of this magnificent spiral-shaped object with hundreds of billions of stars stretching 100,000 light years from side to side. And as you can see, that too is just one galaxy out of billions and billions and billions of others, which in turn form larger structures, groups, clusters, superclusters, and enormous filaments. On the left side here is this so-called Sloan Great Wall that me and my colleagues on the Sloan Digital Sky Survey discovered, and it's like 1 billion light years from side to side. And yet this also is just a small part of an even grander structure, what we affectionately call our universe, which is now, thanks to my wife, appearing on stage here. This is the spherical region of space from which light has had time to reach us so far during the 13.8 billion years that have passed since our Big Bang. And if you promise to be gentle and loving with it, you can play with it a little bit. It's so far, we just flew farther and farther out into space and found more and more stuff. That's pretty intuitive. But what is this weird stuff? These yellow and green and blue colors. What's up with that? To understand this, it's not enough to talk about our place in space. We also have to explore our place in time. Fortunately, that's rather easy by simply looking into the sky, because as we discussed, we see the sun the way it was 8 minutes ago. Right? The stars we might see walking around at night in San Francisco, we're seeing things that happened hundreds of years ago. So if there is someone out there looking back at us, they're not going to see us. But they might see when the Spanish first settled the city. And when we look with really good telescopes, like the Hubble Space Telescope that took this one, we can see here a number of galaxies the way they were billions and billions and billions of years in the past. So we can very directly learn about how our cosmos is, both presently and at various epochs through its history. So what have we learned from studying the past in this way about our place in time and about the history of our universe? Well, we've learned something very surprising. And to understand how surprising it is, I want you to just imagine for a moment that each one of you is a galaxy. And I'm looking out at you into our universe here. And what's really surprising to me is I notice that all of you guys in the front row seem to be in your 90s. You guys here maybe even about 100. And then we have a bunch of 80-year-olds and 70-year-olds and 60-year-olds, and sort of halfway back, I see a bunch of teenagers. Behind you, I see a bunch of preschoolers and some toddlers. And the second last row, I see only a bunch of infants. And the last row is completely empty. And as if that weren't weird enough, the back wall of this room is glowing with a strange glow of microwaves. And to further add to my puzzlement here, you're all blushing. You guys in the front are just blushing a little bit, but those of you in the back are like tomato red. So what's going on with this? What does this mean? This is exactly what we see when we look into the sky. Well, first of all, the fact that you seem to be arranged by age, we can understand quite clearly by just remembering that the farther away we look, right, the longer it's taken the light from there to reach us, so the farther into the past we're seeing. And that's why nearby we see old, mature galaxies. Farther away, we see younger galaxies, and really far back, we see just baby galaxies because they haven't had time to develop and grow. And in the back row, the one that was empty, no galaxies at all, because we're looking so far back in time that they simply hadn't had time to form yet. All there is here is the hydrogen gas and so on, out of which the galaxies would later develop. Why are you guys all blushing? Well, we know that if you stand next to the I-80 and you listen to the cars, they go, ew, ew. They don't sound like, ew, ew. They go, ew. The pitch of sound, the frequency of sound gets lower when the car is going away from you. We call it the Doppler Effect, and many of you have probably heard of this. And it works exactly the same way for light. If you look at light moving from something going away from you, the frequency is lower, which means the color shifts towards the red. We call it redshift. So the fact that you guys are all blushing must mean that all of you galaxies out there are actually flying away from me. The fact that those of you in the back are blushing more, looking redder, that means you're flying away faster. And Edwin Hubble, who we talked about, who was the first person to establish that there are other galaxies, discovered that if you're twice as far away, you're actually moving away on average twice as fast. This is what we mean when we say that our universe is expanding. If you want to know how long ago this sort of stuff started, well, if everything is if you're twice as far, if you want to figure out how long ago was a given galaxy, were you, for instance, right here? Well, all I have to do is figure out how far away you are and how fast you're going and divide one number by the other, right? And if twice as far away means twice as fast, that means we're all here at the same time. So we can do this math, it's very easy. So in about 14 billion years ago, or 13.8 when we do it more carefully, it seemed like pretty much everything was all on top of everything else. So something really crazy happened. We're not sure exactly why. We have a fancy name for it, though, of course. We call it our Big Bang. How that got started is still shrouded in mystery. I talk a lot in the book about the best theories we have for it. But we know a great deal about what happened during the 13.8 billion years since then, because we can see most of that with our telescopes. Now, there's one last thing that was really weird that we saw here that I haven't covered, which is why is the back wall of the room glowing with microwaves? That's because this isn't just empty space. When I was a kid, I thought that this black in these space photos was vacuum. But of course, it must be the gas, which later turned into all the galaxies and stars. And if everything is expanding, a gas cools off when it expands, right? That's how our air conditioners and refrigerators work. So in the past, when everything was squished together, it must have been progressively hotter and hotter and hotter. And if you heat a gas up beyond a certain point, it changes into something else, namely a plasma. Exactly, and a plasma is not transparent. You cannot see through it, so it looks like we're staring behind all these galaxies into an opaque plasma screen. That's what it looks like. And of course, it's going to look the same whatever direction we look in. Look sufficiently far away, we're seeing so far back that it's so hot that all the gas is a plasma. And we can take pictures of the inside of this plasma screen in all directions, and this has been beautifully done by the Wilkinson Microwave Anisotropy Probe satellite NASA sent up. And this is what it looks like. And who's the keeper of our universe right now? Has it disappeared? Turned into gone to a parallel one? Throw it up in the air so we can see our universe. Oh, there, wonderful. That is the same image, of course. We are in the center. You should think of it as us looking at this plasma screen from the inside. And what we're seeing, this plasma is so far away that we're seeing the way this plasma was only 400,000 years after our Big Bang. These are the best baby pictures of our universe that have been taken up until that time. They've revolutionized the field of cosmology. Some people still wondered if they were somehow screwed up, if there was something wrong with them. And the way to test is to build an even better telescope on an even better satellite and see if you can take a picture and it agrees. Just last year, the Planck satellite took this picture. And look at any one spot and see how beautifully they match up, except the new one has an even sharper image. This was 3 megapixels, now it's 50 megapixels. It's really remarkable that we can take pictures of what happened 13.8 billion years ago. In summary, we humans, from back in the day when we looked at these sparkling dots in the sky and wondered what they were, until this kind of precision cosmology, we've come a very long way. But whenever we answer questions in science, it tends to reveal new mysteries. And there's no shortage of mysteries. We've discovered, for instance, that all the atoms that we are all made out of make up only 5% of the stuff in our universe. Oops. So we have no clue really what 95% is made out of. About a quarter of this stuff is some other weird substance, dark matter, that we're trying to figure out what it is. And then there's another 70% or so, which is even more weird, we call dark energy, which is really little more than a code name for our ignorance at this point. But it's going to actually also determine what happens in the future, what this dark energy is, and you can ask me more about it afterwards. So there's a lot of mysteries. We'd also love to know more about what really happened early on, what put the bang into our Big Bang, were there other Big Bangs, what really took place. A lot of things we'd like to know. And to make progress on all of these different questions, we really basically want to do the same thing. We want to make even better maps of our universe. So let me remind you just of how little we've accomplished, so we don't get too arrogant here. This looks like a lot of space, and it is, but let's peel off. Don't peel off the surface of the ball there, because we don't want to spoil the universe. I'll do it here graphically instead. All these pretty plasma pictures were just from the inside surface of this ball. Okay? And all of those galaxies that we flew around in earlier were just the little green stuff in the center of the picture. Less than 1% of the whole volume. So the vast majority of our universe, the region from which light has a time to reach us so far in space, is still uncharted territory. We'd love to know what's in here. And if we can, it'll shed great new light on what dark matter is, what dark energy is, what really happened early on, what's going to happen in the future. And fortunately, there's a really cool technique for trying to do this. You can't just look here and see more galaxies because there aren't any. This is so long ago that they haven't had time to form. But all this hydrogen gas can actually be seen with radio telescopes, because hydrogen gas, turns out, gives off radio waves. They're this long, 21 centimeters, and they get stretched out with the expansion of space, so they're a little bit longer when they reach Earth, which tells us how far away they came from. And with this technique, we can build up three-dimensional maps of all this. And there's a worldwide effort right now to try to do this and basically make vast, awesome 3D maps of our universe. We've had a lot of fun at MIT with my group working on exactly this, and I'm extremely honored that actually 3 of the people who've built this experiment are here in the audience. So can Adrian Liu stand up, and Andy Ludomirsky and Ashley Perko? Are you here somewhere? Yay! So let me show you the awesome stuff that we've done together. Let me teach you in 2 minutes how to build your own radio telescope. It's really easy. So I'm so happy that Andy and Adrian and Ashley are here tonight, because one of the reasons it's just so much fun to get to work as a scientist is to get to work with such awesome and inspiring people. We have so much fun together, and now we're actually teaming up with a bunch of astronomers, as you saw here, from around the country, especially here in Berkeley, which has one of the best groups on the planet doing this, to build an even bigger telescope that uses this technology to help shed more light on this. Now, I open by saying that we have been the masters of underestimation, we humans, and I want you to think big. We've talked about how we've underestimated again and again the size of our cosmos, but also how we've underestimated our ability to understand. And it's really remarkable how cosmology has, even in the short time I've had the fortune to get to be in the field, been transformed from a really flaky philosophical area where you could speculate with your friends over some beer, about what happened early on, into really a precision science. And we have a very quantitative story of what actually happened during the past 13.8 billion years. And that begs a very interesting question. Why is it that we humans have been able to figure out so much about our world? what's the reason for this? It's not obvious that you have a bunch of quarks in the universe and you put them together and they become self-aware and they can actually understand things about things which are much bigger than them, right? It feels a bit like a miracle. So what is it? Well, one of the reasons clearly is that you guys and all of us humans, the human mind is really awesome. One of the things we've discovered is that there are a lot of things out there that are bigger than us, but there are no things out there we've found that are actually more beautifully complex than us. The most complex and elaborate object in the known universe is the human mind that you all have in your heads. So that's clearly part of the answer. But it's not the whole story. Another part of the story is that we've found that our world really hides an elegant simplicity and beauty, revealed by mathematical patterns and shapes. And these patterns have given our minds this incredible ability to use mathematics to predict what's going to happen in the future and even improve it by using technology. We've found the one really good idea in science is to make experiments to look for these patterns. And then when we do experiments, another really good idea is to take all our measurements and look for mathematical descriptions of them. And this is an old idea. Already Pythagoras said that numbers seem to rule our universe. There seems to be something kind of mathematical about it. About 400 years ago, Galileo was so impressed by this that he said that our universe is a book written in the language of mathematics. But where is this math that these guys are all going on about? I mean, I look around in the room here. Do you see any math? Do you even see any numbers? Oh, here's one. No. But I actually wrote that one myself. I typed it into Keynote. So this obviously isn't anything fundamental about nature. So where is all this math? Well, you can see in Galileo's extended quote here that to him, math is not just a bag of tricks for manipulating numbers or a sadistic form of torture invented by school teachers to make us feel bad. Now, he's talking about shapes, geometric figures. And nature is, of course, full of recurrent shapes and geometrical figures and patterns. If you throw something up in the air, for instance, what do you call this shape that it'll move in? A parabola, exactly. And it obeys a very simple mathematical equation. Y equals x squared, if you draw it like this. No matter what it is you throw, it's a parabola. If you look up into the sky, like Galileo did with his telescope, and Kepler carefully analyzed, you find that everything orbits in another shape, which we call what? An ellipse, exactly. It obeys another very simple equation that you see here. And moreover, these two shapes of objects moving under gravity are actually the same. If you look at a little corner of the ellipse here, it's very well approximated by a parabola. And if you throw something in this room and you actually calculate a bit more accurately, it's really going in a very skinny ellipse. So what are the bad habits that I have as a professor is I love to give pop quizzes, unannounced. So don't worry, this will not contribute to your final grade. It's just a diagnostic quiz, so lower your blood pressure. But think about this. Of these three discoveries, the discovery of Neptune, of the radio wave, and of the Higgs boson. Now, what tool was it that triggered the discovery of these three things? Mathematics. You all get an A on the quiz. You could say, if you want to be a stickler, there was the pencil, because they were all predicted through mathematics. Urbain Le Verrier in France was intrigued by the fact that the planet Uranus wasn't moving quite the way it was supposed to, according to Newton's equations of gravity. And he did lots of mathematical calculations, and then he wrote a letter to an astronomer named Gall in Berlin and said, when you get this letter, point your telescope to such and such a place in the sky, and I predict that you will there find a new planet. The guy probably figured that whoever wrote this letter was cuckoo for Cocoa Puffs, but he must have been kind of curious too, because he pointed his telescope, looked, boom, there was the planet Neptune. Just a few decades later, James Clerk Maxwell was studying all the equations known about electricity and magnetism and realized that the math would hang together better if you added one equation and fixed things up a little bit. And he came up with what's now known as Maxwell's equations, which my I was just assigned by MIT to teach a course about this spring, and he studied this. He made a prediction that if you built a certain kind of device, you could use it to send what's become called radio waves at the speed of light and communicate. You could communicate through walls, across oceans, even through empty space. Later on, that was built. Boom. It worked, and now raise your hand if you have a cell phone in your pocket. Mathematics is powerful. And most recently, of course, Peter Higgs took the most elaborate mathematical description we have so far about physics, the so-called standard model of particle physics, and did some really complicated calculations and predicted that if we humans build the most advanced scientific instrument ever constructed in Geneva, and we crash particles together there near the speed of light in a certain way, we will there discover a new particle. You know the rest. It was built, boom, there was the Higgs boson, and he was rewarded with a free trip to my hometown of Stockholm. And those are just 3 examples. It's really remarkable how, with just a small number of mathematical equations, we can describe the vast majority now of all the physical phenomena around us in the world. What's even more remarkable is that my wife, who's sitting here, kindly went along with me putting these nerdy things on the wall in the living room. But I just feel very fortunate. Some people even went further and put the equations on their tombstone. This is what Erwin Schrödinger did with the master key of quantum mechanics that he came up with. And it's not just equations, it's also numbers. In the book, I explain this little bit about this list of 32 numbers, pure numbers with no units or anything like that. And from these 32 numbers, we can now, in principle, calculate every single other physical constant ever measured in the history of science. So you can measure hundreds of thousands of different numbers that tell you things about atoms, for example, what different colors of light come out of it when you do different things to them. Can all be calculated from these numbers. Why is the proton 1,836 times heavier than an electron? You can calculate it from these numbers and the equations that we have. So why is this? Why? Mathematics is very powerful. That's not controversial. Where it gets really controversial, and where people love to argue, is what to make of this. Okay, and in the book, a lot of the stuff I talk about, which I love explaining, is not particularly controversial. I've flagged those certain sections in the book as controversial, so you know, and which things we really don't know. And Eugene Wigner in 1960 said that the enormous usefulness of mathematics in the natural sciences is really something bordering on the mysterious. And there's no rational explanation for it. Some people still feel that there is no explanation for it. Some people feel this is just not an interesting question and we shouldn't ask it. Some people think it's some kind of fluke. Some people think maybe math is just something we humans have invented. But I explore the whole spectrum of possibilities here in the book, and I also explore the opposite extreme of the spectrum, which is that there really is an explanation, and that this really means something really profound. And in particular, I explore the possibility that what it means is that our universe isn't just described by mathematics, but that it is math. Specifically, that we're part of a giant mathematical structure. So what that means in plain English is that our world doesn't just have some mathematical properties, like that things fly in parabolas or whatever, but that it has only mathematical properties. And we know in mathematics that we can often take some complicated math and approximate it by simpler math. So if this is true, what this means is that all the math equations that I showed you that my wife let me put in the living room are just simpler math, which is approximating the true math that maybe one of you folks will discover in the future, the theory of everything, unifying gravity and quantum mechanics, and you'll get a free trip to Stockholm for. Now, this really sounds pretty nutty. It sounds pretty crazy, though, because when we look around in the world, it really doesn't look mathematical at all. And to just make that point a little more clear, I want to introduce you to our dear friend, Mr. Hoggles, who lives in our backyard. He is a groundhog. Actually, he feels that it's we who are living in his backyard, because he moved in first. And if you look at him, and you ask, what properties does Mr. Hoggles have? you might think, well, maybe cuteness, maybe herbivorousness, maybe passion for hole digging, love of grass eating, those are not mathematical properties at all, right? So how can we say that our universe has only mathematical properties? Well, at the same time, though, we know that Mr. Hoggles, and in fact everything else in the world, is made of these elementary particles, like electrons and quarks. And what properties does an electron actually have? Well, as you can see in this table here, the electron has the property -1, 1/2, 1, and so on. We physicists have come up with geeky names for these properties, like electric charge and spin and lepton number, but the electron doesn't care. These are just words that we humans made up. The only properties it has are these numbers, just mathematical properties. And as far as we can tell, the electron is a purely mathematical object in the sense that it has no properties at all, except these mathematical properties. It doesn't have the property of cuteness or herbivorousness, etc. It's just numbers. And the same goes for all the other particles that form the building blocks of everything around us. Everything in space seems to have only mathematical properties. What about space itself, then? What properties does space have? Well, it has the property 3. That's the largest number of laser pointers I can put that are all perpendicular to each other. Of course, we physicists have a geeky name for that too. We call it the what? The dimensionality of space, exactly. But space doesn't care. That's just the word we made up. It has the property 3, a very mathematical property indeed. Einstein also realized that space has some more properties beyond what Euclid envisioned in his Euclidean space. It also has properties of curvature and topology, which mathematicians study, because these are also purely mathematical properties. So if you take seriously this notion that both space itself and everything in space is purely mathematical in the sense that it has no properties except mathematical properties, then it starts to sound a little bit less insane and crazy, that the idea that everything is, in fact, completely mathematical. So to come back to the basic themes we've talked about here, we humans have repeatedly underestimated 2 things, right? The size of our physical world and the power of our human minds to understand it. And I've argued that part of the reason we've been so successful in understanding it has been that we've been lucky. It turns out that nature has all these mathematical patterns in it that our human minds have been able to discover and then use to understand it better and improve things. So what does that ultimately mean for us? Why should we care about this? What does it mean for our future? That's what I want to finish by talking about. First of all, for the future of physics, if this is correct, which it might not be, of course, but it's interesting to explore. If it's correct, I think it's actually very good news. Because if I'm wrong, and there are some properties of our world that cannot be described mathematically, then physics is ultimately going to hit a roadblock. We'll get to a point where there just are no more of these awesome mathematical regularities left to discover. We won't make any more progress. We'll be forever stuck in our quest to understand our world. But if I'm right about this, and there is no roadblock, then there's nothing in principle stopping us from continuing to understand our world better and better. And we're really only limited by our own imagination, which I think would be awesome. Either way, I think it's nice to be an optimist, because there's no better way to fail at something than just convince yourself from the get-go that it's impossible and therefore never even try, right? Now, what does it mean for other things? Well, if there is no roadblock and everything can be understood in principle, then even things which we certainly don't understand now, like, for example, consciousness, means we could, in principle, if we're clever enough, understand them too. For example, if consciousness can be understood as particles that move around in beautifully complex patterns that process information some way, then I too could be described mathematically. You could think about about the mathematical shapes that all these particles make as they move through space and time. If you take a boring dead object like a rock, all the particles are stuck together, so they just form a very dull pattern, like a bunch of spaghetti, uncooked, stuck together like this. Whereas if you take a living object, if you think about all the electrons and the sodium ions and so on moving around in your brain as you're thinking, they make an incredibly complicated pattern. Of course, you have to imagine this with 10 to the power 26 instead of just a handful of strands. It's an incredibly elaborate braid pattern, so complex that there's nothing like it in the known universe. That's about the future of science, the future of physics. But what does it mean for the future of us, the future of life? So our human minds, right, we have the power not only to understand the world, but also to shape it and improve it. So it's very interesting to ask, well, what are we going to do about this? What's around the corner here for humanity as we head forward? This is something that, as you know, people have thought endlessly about and written endlessly about, and there's a wide spectrum of ideas out there. For example, there's nothing in the known laws of physics that prevent life from ultimately spreading off our planet and helping more of our universe coming alive. And we also have a lot of time, a lot of potential for doing this, because we know now that we're not limited to just the next 50 years or the next 200 years, but we have billions and billions of years at our disposal and 10 to the power 57 times more volume to play with than we thought. But then, of course, a lot of people have also pointed out that we can also use our technology for other things, like wiping ourselves out in various creative ways. We could have an accidental nuclear war, or... Did anyone see the movie Her? Raise your hand. Some people have speculated that if we build machines that are more intelligent than us, that could either be super awesome, like Ray Kurzweil thinks, or it could wipe us out completely. We have other various creative ways of messing up our planet. There's no shortage of threats that we face. And I talk in the last part of the book about bringing us back and asking what this means for us. And it's interesting, if you take all the most common risks that we face and you sort them by how far into the future they're most likely to wipe us out, it's quite interesting that all of the most urgent risks, the ones that have the potential to wipe us out the soonest, are risks or threats not created by our universe towards us, but threats that we have created ourselves. And in fact, if we manage to deal with this and avoid wiping ourselves out, there are actually very interesting technological solutions to pretty much all of these problems. You can ask me about afterwards how to deal with the asteroid threat or the fact that the sun is going to get too hot. I'll be happy to share that. So I warned you for truth in advertising that I have a lot of bad habits. One is I like to give pop quizzes. Another one is, as a professor, I just can't resist the urge to give out grades left, right, and center. So I decided to give humanity a midterm grade for Risk Management 101, for how well I feel we're dealing with this stuff. So I asked some friends, what do you think? What grade should we get? And some of them said, well, I don't know, maybe a B+. Sure, we've played kind of Russian roulette a few times, maybe like the Cuban Missile Crisis and a few other dumb things where we probably took greater risks than we should have, but we're still here. That ain't bad. Maybe not an A, but B+. But I actually decided to give us a D-. First time I've ever had an applaud for giving someone a D-. I gave it to all of us. And you should know I'm actually known at MIT as a very lenient grader, too. So I thought I should justify this and explain a little bit what I mean by that. If you ask different people how likely they think it is that we're going to wipe ourselves out in any given decade, you get a wide range of answers. Some people think it's very unlikely, maybe 10 to the 1 chance in 10,000. Other people think it's maybe a 1 chance in 10 per decade. And if you're convinced that that the apocalypse is coming, as it says in the book of Revelations, and everything is going to end anyway in 30 years, like heard a frightening senator from the Bible Belt say on TV recently, that's why we shouldn't worry about global climate change, because it's all going to end anyway, then maybe a B+ isn't so bad. I'm so glad I'm giving this talk in San Francisco. But I just realized this might be televised. It's going online, so I might get some hate mail now from... Oh, well. But so that's a sort of a standard perspective, right? If we look very short term, think about this planet, the next election cycle, It's maybe okay taking these kind of risks. But if you take the cosmic perspective, that we humans, that self-aware life here has so much potential on this planet, beyond, and not just for 100 years, but for billions of years, why then I think it is just absolutely reckless to keep rolling the dice like this over and over and over again. It's not going to last for billions of years. And just to drive home the point more clearly, if I ever give a low grade, the student will always come back and ask me to justify why. So let me justify it like this. Let me ask you, which of these two people is more famous? It's pretty clear that more people on this planet have heard of Justin Bieber than about Vasily Arkhipov. But let me ask you another question. Which one of these two people should we thank for us all being alive here tonight? Because he single-handedly stopped a Soviet nuclear attack during the Cuban Missile Crisis. Well, I'll give you a hint. He's not Canadian. And this is pretty screwed up. Priorities, I feel, for our species. This is why I give a D-. We consider that little minor detail of allowing us all to be here tonight so unimportant that we don't even pay as much attention to him as this young man. And why is it then that we humans devote so little resources and so little intellectual energy towards thinking about these big threats? Especially when we actually have so much potential to do something good about it. The first answer I often get is, oh, we just don't have the money. So let's look at some numbers. There are some organizations I talk about in the book which are really trying hard to do something constructive about some of these risks. The Union of Concerned Scientists is probably the best funded one in the US, funded by a lot of generous people like you in the audience give to them. And they get $20 million per year. So let's shrink that down and let this tiny area here represent $20 million. And let's look at what we spend on various other very important things, like cosmetic surgery, $10 billion per year. Air conditioning for US troops, $20 billion per year. Smoking, $100 billion per year. And don't get me wrong here. I'm a strong believer in personal freedom and personal choice. If my friends want to light up, fine by me. But I'm not going to take it if one of my friends comes and says that we just can't afford cutting the size of the cigarette box by that tiny area of this, to double this. Right? That's clearly not the real reason that we're not spending more effort on things like that. And I didn't even fit the biggest budget item on my screen, by the way. Only part of it fit. We had to actually have to shrink it more to fit our military expenses here. So if it's not the fact that if it's not the lack of money that's preventing us from being more focused on being good shepherds of our planet and safeguarding our future, what is it? Well, another answer I often get from people is that it would simply be irresponsible for us humans to devote a lot of resources towards risks that haven't been proven. And if you think about that for a moment, I think the easiest way to see the logical flaw in the argument is to just imagine for a moment that you're in a store buying a stroller for the baby of a really good friend of yours, and the salesman comes up and says, hey, I got this really nice, very robust baby carriage here for $49.99, and we've sold it for over 10 years. There've never been any reports of any safety problems with it. But then I have this model for only $39.99. Yeah, I know there have been some news reports of it sometimes collapsing and crushing the baby, but it's kind of unsubstantiated. And frankly, nobody's ever been able to prove in court that these deaths, these babies, were actually due to any design flaws by the manufacturer. And hey, it's 20% cheaper. Wouldn't it be irresponsible to spend 20% more money on a risk that isn't proven? So if you feel that it's silly to say that it's irresponsible to spend money on risks that aren't proven, but rather that it's irresponsible to not spend money on risks unless we can prove that they're not dangerous, then you would obviously also feel that that should apply not only when there's one baby at stake, but when we're talking about every baby on the planet and every baby that will ever live in all future generations. So in summary, when we look ahead at the various options that we have for life, what I've tried to convince you is that even though we humans are small, the fact that the cosmos is so vast means that we have much, much more potential, first of all, than we thought we did. And also, the fact that we've again and again underestimated the power of our minds to understand the cosmos and to improve it, it means that we've also really, really underestimated our ability to improve the world and to make a difference. So let's make a difference. Thank you. So we have lots of time for questions. So the way this will work is whoever manages to attract the microphone to you gets to go first.
First question is right here in the center.
You've used the expression several times in your talk that not only understand the universe, but improve it. And you don't use words loosely. So I'm curious if you'd elaborate a little bit on how you think we humans have improved the cosmos, because I personally don't see that we've improved it. I agree we've certainly gained tremendous understanding of it.
I was thinking is not that we've rearranged the planets or anything like that, but the fact that we've managed to improve our local environment of the cosmos quite a bit. The life expectancy for us in this room is just dramatically better than it was 10,000 years ago, because through science, we've understood better how our bodies work, revolutionized healthcare. That's just one small example, which I think we would all feel is an improvement. Of course, you raise a very important point there, that technology gives power, and anything that gives power is always a double-edged sword too. It's often the same technologies that enable us to make life better that also give us more potential to mess up and do terrible things and even wipe ourselves out.
Does anyone on this side have a question that I can get to easily? Okay.
Could you tell us about other universes?
Oh, I'll be delighted to. So can we first have our own universe up on stage briefly? Who is the keeper of the cosmos? Thank you. Awesome. Nice. So before we go to other universes, let's just remind ourselves of what we mean by our universe, because when I was a kid, I thought our universe just meant everything that exists. But that's actually not what we mean as astrophysicists. We don't mean all of space. We simply mean the part of space shown here that light has had time to reach us from so far during the 13.8 billion years since our Big Bang, because that's the largest part of space that we can see anything from, even with the best telescopes you could possibly imagine. Okay? So if space is actually even bigger than this, then if there are other universe-sized regions out here, with galaxies and such in them, we can't see them, but you might be able to. You could still maybe see the light if you waited for another 10 billion years for the light to reach us. Okay? So the question is there more space out there? Well, Euclid, over 2,000 years ago, assumed that space kind of went on forever. That's what I used to think when I was a kid also, because it's kind of hard to imagine how it wouldn't. Would there be like a sign saying, warning, space ends here, mind the gap or something? That would be kind of weird. What's on the other side then? But then Einstein actually came along and said that actually physical space could be not infinite, even in a less silly way. I talk a lot about this in chapter 2. It could be that, like in some of these old computer games, like Space Invaders, you just go really far in that direction and find that you suddenly return from the other side. So it's ultimately an experimental question, actually, how much bigger space is. We can't go out and look. We have at these places. But it turns out that the best theory we have for what put the bang into our Big Bang in the first place and made this big expanding space, a theory known as inflation, which was pioneered by Alan Guth and by Andrea Linde, who works just down the road at Stanford, and their colleagues. It actually predicts that space is much bigger than the universe that we can see, maybe even infinite. And that's a scientific theory. It's a mathematical theory. It's made a whole bunch of other predictions that I've worked very hard on testing by looking at these interesting patterns you see in these baby pictures. And it's the most popular theory we have. So if you take it seriously, it predicts that there's just much more space out there, which means there are all these parallel universes with galaxies too, disconnected from us, where far, far away, maybe even, there's another lecture like this taking place. And this is actually just one example of several where we humans have realized that maybe there's more to reality than the part that we can see. Another one is when we've studied the microworld of quantum mechanics, we've discovered this weird fact that these electrons and quarks that we talked about can actually be in several different places at once. We can test this in the lab. It's quite accepted that they can. But where it gets controversial is the fact that we're made of these particles. So if my particles could be here and there at the same time, why can't I? And why do you never see that if you're sober? Well, as I talked about in the book, it was discovered in 1970 by a German physicist, Dieter Zeh, that there's a sort of censorship effect in quantum mechanics that prevents you from seeing these other sort of parallel worlds. And in the simplest and most bare-bones version of this quantum theory, which you can also test in ways I can talk about later, it actually predicts that in some situations, our reality sort of, loosely speaking, branches out into different parallel realities that become unaware of each other. So if you're like, shucks, I got a parking ticket, you might figure, well, there's a parallel universe where I actually didn't. But then you might realize also that there's another parallel universe where you got towed. So you win some, you lose some. But the bottom line is, even though this at first just sounds like crazy philosophical speculation that has nothing to do with science, we have to remember that parallel universes are actually not a theory. They're a prediction from certain theories. So we just have the basic logic. If A implies B, and we take A seriously, then we have to take B seriously. I talked about how inflation theory is like that. We take it seriously. We take Andre Linde seriously, so we take the predictions seriously. We take quantum theory seriously. We can test that theory, and we can try to build really big quantum computers, and if they can one day solve math problems which would take longer than the age of a universe to do on a normal computer, and if they can do it in 5 minutes by tapping into the power of all these parallel universes, that'll make us more convinced that those parallel universes actually exist. But it could also turn out that we try to build these machines and we discover that actually the simplest equation of quantum mechanics, the Schrödinger equation, actually doesn't work because there is some extra math that was missing. And then we've killed off that theory, and with it we've ruled out all the parallel universes as well. So it's in that sense that it's an interesting science question to talk about this. And because the experiments are getting so much better, the rhetoric about parallel universes has shifted a lot. It used to be that people thought this was just totally flaky and had nothing to do with science, and the people who didn't like this, which were most scientists, would say, oh, this makes no sense, and I hate it. But nowadays, because of all these experiments which can test these theories, things have really changed a lot. A lot of scientists are taking it seriously. It's moved from being considered just philosophy to being considered simply very controversial stuff that we actually discuss at physics conferences. And the people who don't like it instead say, I hate it, which is tacitly acknowledging that actually it's a science question. And what's going to be really cool down the road is not flying to these parallel universes and trying to look at them. We can't do that. But to test this inflation theory better. We have, in September this year, this Planck satellite that took these amazing pictures of this, for instance, is going to release even better data. And it might be that this year or within a few years, we'll see another kind of signal in polarized light of these microwaves, which could prove the smoking gun evidence that Alan Guth and Andre Linde are right, and give them the Nobel Prize, almost certainly. If that happens, we'll take this idea much more seriously. If instead we get data that really suggests that this whole inflation idea is wrong, we'll take it much less seriously. So it's going to be really fun to see how this develops. All right, back to this universe again.
Next one's back here in the center.
You've described about 30 different physical constants that describe the mathematical structure of the universe. I read a book about 20 years ago by Martin Rees, who was the royal astronomer in Britain at the time, the book was called Just Six Numbers. And it mentioned 6 constants or ratios, of which I only remember 2. One of them is 3, the number of dimensions. The other was the ratio between gravity and the electrostatic force. And for example, his postulate was, his question was, why is it that these numbers are just such as to create a universe that is favorable for life as we know it to arise? For example, if gravity were stronger, we would be crushed. It would be hard for larger life forms to develop. If gravity were weaker, there would be no atmospheres. So does this imply, so stepping back and asking the bigger question, which is why are these numbers what they are? Most of them are not ratios of rational numbers. They're not integers. You know, are these arbitrary numbers selected by a creator who wound up the clock knowing that the clock would create life? Or are there multiple universes, each with their own set of constants?
That's a wonderful, wonderful question. First of all, I'm glad you mentioned Martin Rees, because he's a very good friend of mine. And I once asked him why he picked only 6 numbers in his book, when there were actually more. And he said that he did it because he felt the book would be too long and complicated otherwise. But this list is fascinating, because it's really the complete list of these numbers with decimals on. And it begs the question, you know, why those numbers? You know, why is the proton 1,836 times heavier than the electron? You know, why not 2,014 times heavier? It's a perfectly fine number. And as you mentioned, what's really intriguing is if you imagine that there are all these knobs that you can twist to dial in what these numbers should be, you want to be really careful when you touch these knobs, because most of them, if you mess with them just a little bit, life as we know it ends. The sun explodes or something like that. For example, the 2 most scary knobs that you should really not fidget with are this one here, the quadratic Higgs coefficient. It's sort of weird number, -2 times 10 to the minus 34. If you start messing with that by just a little bit, suddenly either the protons in your bodies will decay into neutrons. So all your atoms stop functioning, and puts an abrupt end to this lecture. Or if you turn it a little bit the other direction, it gets even worse, and I wouldn't try that either. In fact, if you change it even by just 1% in either direction, it turns out that the stars that made all the atoms in us, the heavier ones like oxygen and carbon and so on, would either make like hundreds of times less oxygen or hundreds of times less carbon. So this we should not mess with. This one is even more fine-tuned. The dark energy density, well, look what a weird number. Most of these numbers are of the order of 1 or 10. But this one, look, about 1 times 10 to the minus 123. So it's like tuned to 123 decimal places. And it turns out if you change it by just a puny amount, make it a little bit bigger, there are no galaxies at all. You make it a little bit smaller, it goes a little bit negative, you just make a giant black hole, which also would put a bit of a damper on our lecture here. So this begs the question of why is this? It's not controversial that you shouldn't mess with them. And you've already mentioned the 2 of the 3 most common reactions to this. One reaction people have is, well, it suggests that somehow our universe was designed. I know it could be some sort of religious creator, or maybe if you want to go more sci-fi, maybe someone simulated our universe and thought this was the most interesting thing they could come up with. You know, there is another common reaction, which is just, okay, that's just a brute fact. It's the way things are. Let's not think about it. But that's also a very unscientific response, because unexplained coincidences are exactly, in science, equivalent to saying that a theory is ruled out. You know, you could always say, okay, we made this measurement. We found that only 5% of the stuff in our universe is atoms. Well, you know, if you were to redo this experiment, the Planck satellite, a quadrillion times, one of those quadrillion times, random fluctuations would make it look like it was all atoms. So you could say maybe we're just unlucky. Maybe it's just a fluke that we... But when we say that something is ruled out at 99.9999% significance theory, we mean exactly that it would require a huge coincidence for it to fit the data. So that's not so cool. The third explanation is the one that you mentioned, which is to say, suppose that space is actually much bigger than our universe. And suppose that these constants aren't really constant. but that they can vary from place to place. So you have a large universe-sized region where this dark energy density is a little bit higher, and somewhere it's a bit lower. Okay? What does that do? Well, that means that in most places in space, there just are no galaxies at all. So if you ask what kind of cosmological constant are you going to observe if you measure it, if you observe it from, if you go look from a random galaxy, you're going to get pretty much this value, because right? It's only in those places in space that there is any galaxies to have. It's kind of like if you find that you're living in the Sahara Desert, you shouldn't be so surprised if you're living in an oasis, because that's probably the only place where there are people, right? And Steven Weinberg used this kind of funny argument, the famous Nobel laureate Steven Weinberg, several decades ago to predict that one day we would actually measure that there was dark energy and that there would be about this much of it. And most people figured, well, he's just, one of those old professors who's going all philosophical and soft in the head. But then, as you all know, later on, by studying distant supernovae, astronomers, including Saul Perlmutter here at Berkeley, discovered that actually we have dark energy. And guess how much we have? We have about this much. All right, so Steven Weinberg actually predicted this. So he took this multiverse idea, that there is this bigger space, and actually made a prediction, and it actually worked. And this is actually the only successful explanation we have so far of a scientific nature for why it is this way. And you can also make use the same explanation to explain why this number is the way it is, because again, if this could vary from one part of space to another, which it probably can, if anything like string theory is right, then it's not surprising that we happen to live in one of those rare parts of space where there are atoms. So the picture this paints is that actually our universe is kind of like the Sahara Desert, if you zoom out and look on a really large scale. We live in this enormous space, and most of it is actually very inhospitable and totally dead. Nobody there. But then there are these very rare oases, which are just awesome and perfect for life, and we are in one of them. And if you think this sounds kind of strange, it's not really any different from what we actually see when we look around us more nearby, right? We flew around, we looked into space nearby. Are you surprised that we don't live in the center of Earth or in the center of the sun or in the middle of an intergalactic void? No, it's not very good to live there. We happen to be in a very special place. We happen to be inside of a galaxy, in the solar system, right on the surface of a planet, not inside where there's much more volume, and not like like the Douglas Adams whale, in free fall, 20 kilometers above the ground. We're not surprised. We are alive, so we find ourselves where we can be. This is also controversial stuff, and but we keep learning more about this now when people go ahead and figure out what happens when we try to change these numbers. And it's turned out to be a pretty generic feature of not just of string theory, but also of the main competitors of string theory, like loop quantum gravity, that the equations that are supposed to give these numbers as solutions, they tend to have many different solutions. And then this inflation process, which makes space, is very violent, and it tends to create parts of space where each of these different solutions are realized. It's a little bit like, I sometimes like to imagine that I'm a fish who spent my whole life living in the San Francisco Bay, and I think that water that I swim around is just space, because I don't know any other kind of substance. I think it's empty. But if I'm a really smart fish, I could realize by studying the properties of this water that it's actually made of these atoms, and I could realize that actually the equations for water have 3 different solutions. The liquid kind, it's the one I'm swimming in, and also the solid kind, ice, and the steam, the gaseous kind. You might laugh at this fish, but it seems now maybe the last laugh is on us, because it seems like this, what we thought was empty space, is also some kind of substance. And maybe it can freeze and melt and so on, which would correspond to different values of these numbers. So it's giving a different perspective on not just how vast space is and that it might be more diverse than we thought, but it's also giving us this notion that what we thought was boring empty space isn't so boring. It's actually something which can be in many different ways.
Next question.
Okay. So we obviously, I'm here. We obviously, here. Hi. We obviously are in the discovery mode, right? And I'd like to know if we address some fundamental questions that human beings are asking to themselves. Is a mathematics today allow to answer some of these questions? For instance, is the mathematics telling us is there was a beginning of time? Is a time has had a value 0 sometime in the past? That's my question.
Okay, that's a great question. So what do we really know about time? Did it, for example, have a beginning? And we can also ask, is it going to have an end at some point? We've always had some things we knew, and then there have been some things we had no clue about. So there's always been a frontier of our knowledge, and what we've succeeded in doing is pushing this frontier of our knowledge farther and farther back. So now we have a pretty good idea of what our universe was like back to the first second or so. And if we make this great discovery that I was saying could happen within the next few years, giving a Nobel Prize for inflation, it'll push it back even farther. But what happened before that? Was there sort of a beginning of time? Well, we have to ask, what is time really? You know, to a physicist, in practice, time is something we measure with clocks. But a clock, we think of it in a very broad sense, any kind of object that has a repeating motion. You know, my grandma had one of these old pendulum clocks where the pendulum went back and forth. Today, in the best atomic clocks we have, we look at atoms themselves, which are vibrating, and use them as clocks. But if you imagine a really, really extreme situation back in our early universe when things were just a total mess and there were no atoms, there was nothing that was repeating at all, suppose it was just a big hot mess where nothing was even changing at all, then we would, first of all, lose the ability to define any kind of clocks. And it becomes even a little bit unclear what we even mean by time flowing. I mean, if nothing's changing anyway, what difference does it even mean to say that there is a time? Moreover, we also started questioning the sort of fundamental nature of time by realizing that space might not be so fundamental. We realized that even though we can measure things pretty accurately in this room, we probably can't measure anything. We've never measured anything to better than 17 decimal places in all of science so far. And we certainly can't measure distances to better than about 34 decimal places, because below that so-called Planck scale, it seems like space itself is just some weird fuzzy stuff, quantum bubble bath, which doesn't have any of the properties that we normally associate with space. And then Einstein said that, well, time and space are really, very similar beasts. So we have good reason to believe that at some fundamental level, when things were really weird back here and extreme, maybe neither space nor time, as we understand them, have any meaning. And maybe both of them actually just emerged as really good approximations to something ultimately deeper and more fundamental that we don't yet understand. And maybe one day in the very distant future, the same thing will happen again. And the time and space that we know and love will, in some sense, dissolve and stop being good approximations to whatever the true, more fundamental underlying reality is. We, of course, don't know what the ultimate final answer to any of this is. If you can figure out how it works, you should immediately publish this, because you're going to have the correct theory of quantum gravity, which will definitely give you a trip to my hometown. But I'm willing to make a prediction that if we ever are able to find out the correct theory of quantum gravity, really, the master key to understanding it is going to be to answer your question and really understand more deeply what is time.
We have one final question from a very patient young man right here in the middle. You want to stand up?
Why did the Big Bang, what was before the Big Bang? The answer is, of course, nothing, but in that case, if there was nothing before the Big Bang couldn't have been created.
That's a wonderful question. And I love it when somebody who is much younger than me asks me a question that I don't know the answer to. What I want to say is two things. First of all, I really hope that you decide to study a lot of science in school and become a scientist, because then maybe you can ultimately answer this. Second, I want to say that when we try to answer this question, we have to be very open-minded and make sure that in asking it, we're not already making some bad assumptions which will prevent us from finding the answer. If we ask what happened before the Big Bang, we're kind of assuming that there was a before, right? That it makes sense to even talk about time here. And that ties in beautifully with, so your question ties in beautifully with the previous question we had. How did the time kind of have a beginning? We have to be open to the idea that maybe in the distant past, reality was just very fundamentally different, so that effectively the whole notion of time stopped making sense. And maybe there was no before. So I would rephrase your question when you go and solve it, hopefully in your future career, to saying, what was it that really, really happened early on? Thank you. Thank you. Thank you. And if any of you had some really burning questions you didn't get to ask here, just stick around and hopefully I can answer them after the book signing, okay?
And Max will be signing just outside in just a moment.
Thank you so much.
Thank you.